Welcome back. This is the second and the final video on sort merge bucket series. In the last video, we understood about aggregates. In this video, we will continue with joins. There are a lot of cases where we need to join two or more than two data sets. Let's look at some of those situations. The first one is normalization. Let's say we have one table, which is orders. It contains the ID of the customer who made the order, along with the ID of the order, the country where the customer belongs to, age of the customer, and order value. If we have this table in OLTP, like MySQL or Postgres database, and we have to update a specific record. Let's say we want to set the country of user 109 as the US. Well, there are 3 records in this table which will need to be updated. All these 3 records belong to user ID 109. At the moment, this user has country as Australia. Let's say the user has moved to US and we have to update that in our table. We will be updating 3 records. This was because the orders table contained some information about the customer as well as for the order. This may not be the design pattern or the data layout pattern you would like. Most often, what happens in those OLTP systems is we deconstruct or we decompose this table into 2 separate tables. One which contain only orders, which has order related information like what was the ID of the user, ID of the order, what was the ID of the user, what was the value of the order, and how many items were purchased, and things like that. And another table where we have information about the customers, like customer ID, age, country, and so on. By doing this, we end up having 2 different tables, one containing just order details and other containing customer details. Now, if we have to update the country for user ID 109, we end up updating just 1 record instead of 3 as in the previous case. So this kind of concept, also called as normalization, there are different types of normalization. There are different normal forms. This is one of the example of the normalization. What happens is when data is ingested into the analytical environment or into the OLAP from OLTP, usually there is 1-to-1 mapping in the data lake across the data sets, and we end up having 2 tables in our data lake, one for the orders and one for the customers. And in order to get the complete picture, like I want to know from which country, how many orders were made, if we have to answer things like that, we will have to end up joining these 2 tables on the customer ID or the user ID. Let's take a look at the second case where joins are used. Assume we have a table which contains customer ID, order ID, and the value of the order, along with a field called IP address. IP address essentially helps you get the location of the user or location from where the purchase was made. Many a times, this IP address is a sensitive field. It has to be handled with care. We cannot store the IP address in the raw form as shown here because of compliance and regulatory reasons. However, we can store the IP address in encrypted form and we can decrypt that whenever it is needed. The idea is do not store these sensitive fields in their plain text or raw form. Rather, encrypt it and have access controls around who can decrypt it. So one way to achieve that is to have one encryption key, which is same for all the records. Well, this is possible, but for many reasons, this is not practical. One of the reason is if we want the information for a specific user to be deleted, if you follow GDPR, a user has got the privilege to get forgotten. You may choose as a user that you want to have all your sensitive data deleted, removed, or discarded from all the data processing systems of an organization. If we have to do that, we will have to travel through a lot of data sets, and we will have to handle large scale data, maybe in terabytes or petabytes, and delete those records for a specific user when the user says so. This is not practical. Theoretically, it is possible, but this will be an uphill task. Scanning through all the possible data sets and then deleting those. There is a challenge in deletions as well. OLAP systems are not optimized for row-level deletes. There are possibilities, but that's not their strength. It's not something they are optimized for. So, an efficient technique is to have an encryption key for each user. And when the user says, I want to be forgotten, I want my sensitive data to be discarded, in that case, we delete just one record from all the keys table for that user. By doing so, there will be sensitive data stored for the user, but it will not be usable if that data is encrypted. Let's see an example. Let's say we have this table where IP address is in plain text, IP address is a sensitive field, and we have a keys table where we have encryption key for all the users. Every user will have a different encryption key. By joining these two data sets on customer ID, we can encrypt the IP address. And if we have to retrieve the original plain text value back, we can again join these two data sets and we can decrypt the IP address. In this case, if let's say a user 102 says, I want to be forgotten, I don't want my sensitive data to stay in the company's data system, we can remove just one record that is the key for that user. And now when we do any join, maybe a right outer join, maybe an inner join or a left outer join, no matter what join we do, the sensitive data of that user will stay, but it will not be usable because it won't be decrypted anymore. If we do inner join, then this record won't get matched anyways. So this is how the final output will look like. If we do an inner join, we won't be able to get any sensitive data back for that user. So this is again another example where joins are useful or joins are widely used. The other example of join or the other situation where joins are used is to relate data which is generated by different parts of the application. Let's take an example. Assume we have a music providing service. You can imagine something like YouTube Music. Whenever a user registers, there is a user registration data set which is created based on the event, like what is the user ID, at what time the registration was done, and from where the user has arrived. Has the user come to our application via Facebook advertisements or via Twitter, LinkedIn? What is the source? Now, when this user does play any track, any music track, in that case, another event is generated which contains the user ID, which track was played, and for what duration the track was played. So you see, it's the same music application, but different features of the music application are generating different data sets. And then there are use cases to relate these two different data sets. For example, we want to know that how many users are coming from a specific registration source. In that case, only user registration data set will be sufficient to answer that. But if we want to know that what is the lifetime value of the users coming from Facebook, in that case, we will have to check what is the registration source of the user, and we will have to join with track plays, like how many tracks are played by the user. Is the user a free user or a premium user? How often the user plays a song? Is the user one of the daily active user or one of the monthly active user? When the user leaves our platform, and so on. So we have to join data from different parts of the application. Or better say, we have to join data which is generated by different parts of the application. Now, one more situation where joins are used is when you have some data set which you do not own, rather you import from external sources. So let's say we have a table which contains customer ID and order ID and what was the value of the user and the currency of the user. If you have a global application which is used across different countries, people may purchase in different currencies. And in order to make things uniform, we need to have access to the conversion rate table, that on that particular timestamp, what was the conversion rate of USD to other currency, or what was the conversion rate of a euro to dollars. So this is the data set which contains that conversion, like USD to USD or euro to USD, and based on certain timestamp, there could be certain conversion rate. This data set may not be produced by your company or your organization, and this is something you import from outside. Again, you have to join these two data sets or these two tables in order to translate all the order value to a common currency. That common currency can be dollar, euro, pound. That's not the point. The thing is, in order to make things uniform, you need to join the order table with the conversion table. Now, let's come back to our example on which we will develop intuition. Let's say we have sum of orders. For every user ID, we know what is the total order value. This is the data set which we already generated as a part of the aggregations in the previous video. Now, we have one more table which contains the country of the user. And we would like to join these two data sets so that we have a wider view of from which country how many sales are happening. In order to join, we need to find matching keys. Based on the type of the join, you can produce output on mismatch also. That falls under the outer join. But joins, to develop an intuition, it is essentially a lookup. You check whether one key in one of the data set exists in the other data set or not. How can we do that? The naive way is, for each record in one data set, try to find if there is a matching key on the other data set or not. So if we look at the first record of the sum orders, we try to match whether there is any record in the customer's data set with the same key or not. The key over here is the customer ID. The key is the field over which we are trying to join two different data sets. So we match it with the first record, there is no match. We match it with the second record, and then there is a match. So we can output user ID along with what is the total order value and the country. We have access to fields from both sides. And we continue this. There can be there can be zero matches, or there can be more than zero matches, 1, 2, and so on. So we have to look across all the records of the second data set. We repeat the process. So essentially, we match one record with all the records of the other data set. And we repeat the process for all the records in the first data set. So for user ID 102, we check if there is any match or not. If there is any match, we generate the output. And this process is repeated for all the keys. If there is no match, then there will be no output for the inner join. And so on, we end up generating our final output where we have all the fields coming from left as well as right data sets. Now, let's take a look at the footprint. Overall, the runtime will be a multiplication of the number of records on the left and the right side. This is because for each row, for each order, we match against all the possible customers. Storage will be constant because we are not storing anything in the variable. We just take a look at if there is a match or not. Maybe we can have a Boolean flag for match as true or false if you want to do outer join. But in either case, the storage footprint will be minimal, but the runtime will be quadratic. So with this approach, it is very simple to reason about joins. It works on equality as well as non-equality join conditions. There could be some join conditions where you want to produce an output if the keys do not match. It's not very common, but for those cases also this approach or this procedure works well. The downside is it is time consuming. Let's take a look at an optimization. Now, if the joins are lookup, there is one data structure called as hash map, or which has an implementation of hash map, or in Python it is called dictionary, which is very optimized for lookup against a particular key. So what we can do is, for the customer's data set, we can generate a map from this data set where key will be the user ID and value will be the country. We end up having this map. Now we go through each record of the sum of the orders, or the sum orders one by one, and we see if there is a matching key in the hash map or not. So for the first record, there is a matching key, we produce the output. For second record, again, there is a matching key, we produce the output. If there is no matching key, there will be no output for the inner join, as is the case with this user ID. So this way, we again iterate through all the records from the left data set, and we try to find if there is a match or not. This approach is optimized. This will give us the same result as in the previous case, but this is much more optimized. The runtime is linear because we iterate through left data set record by record. For the right data set, we have already a hash map, so we need not to scan through all the keys. Finding a key in hash map is a constant time lookup operation in most of the average situations. However, there will be one more linear time added in the runtime because of the construction of the hash map. So when you construct the hash map, you have to iterate through all the values of the right data set. But overall, the runtime will be linear. It won't be quadratic. The downside is the storage cost will increase because you have to keep all the hash map content in memory for the right data set. We can also flush the content of the hash map to disk, something like a Sparky file format, but that will hamper the runtime performance because looking up against a hash map which is backed by disk is less efficient than looking up against a hash map which is backed by RAM. So this is very efficient if data set on the right side can fit into memory. It has optimized runtime. However, there are some downsides. Some of the joins are not very feasible, like a right outer join on the same setup will be possible, but it is not that efficient. Similarly, full outer join is also not efficient, though it is possible. If None of the data sets can fit into memory. This approach is not practical. And this works only for the equality operator, which is okay because most of our join conditions are based on equality operator. But in case you happen to have a join operator which is on non-equality, this approach will look very, very similar to the first approach, where you end up comparing one row from the left data set with all the rows on the right data set. Now we will take a look into sort, merge, join. Well, this is our core idea of the whole video. Before we go for the sort, merge, join, let's see what happens if both the inputs are sorted on the join column. So we have sum of orders and customers, both are sorted on the customer ID. In this case, what we can do is we can maintain 2 pointers, one on the left data set and one on the right data set. And we will iterate through both data sets in sequence. There will be no nested loops, assuming there is no duplicates. This concept works equally well if we have duplicates with a small modification. The runtime does not change much even if there are duplicates. But it is easier to develop intuition assuming none of the data sets have duplicates. The same concept, as I said, can be applied even if data sets have duplicates and runtime does not change much. So let's continue with no duplicates on either side. So we have 2 pointers which we will maintain, one on the left side and one on the right side. And we will compare the key, which is the customer ID. Whichever key is smaller, we will increment that key, we will move to the next record. Because they are sorted, if any key does not match, then we will try to increment the smaller key to possibly find a match. We will see this very soon. If there is a match, we will produce the output. So this is how it looks. Start with left and right at the top of each data set respectively. Iterate till one of the data sets is completely scanned. If left and right keys are the same, we will output the result. And we will increment left and right pointers to the next records. If left key is smaller, we will increment the left key to the next record. Because the current key is not matching, maybe next key could match because of the ascending order sorting in this case. And similarly, if right key happens to be smaller, then we increment the right record, the right pointer, and we do not produce any output if it is an inner join. Again, things will be a little bit different if there is an outer join and if there are duplicates, but the core concept remains the same. Let's see that in action. So we have left and right pointers pointing to the first record of the both data sets. Here, the key matches 101 on both sides. So we generate the output taking values from both data sets. We can select if left and right data sets have multiple columns, we might not be interested in all the columns. In that case, we can select which columns we want from the left side and which columns we want from the right side. Well, we have access to all the columns from both data sets. So we are free to choose any column we want. So here the output will be 101 with values coming from both sides, and we will increment left and right pointer to point to the next record in both data sets. Now, when we increment the pointers, again, there is a match. So we will produce the output and we increment. Again, there is a match. We produce the output. Oh, there is a mistake here. It should be output. The key is 103. Sorry for that. So we generate the output. Next, we do the same. Now when we increment the pointers, the keys do not match. Here, 105 does not equal to 106. But because 105 is smaller, we will increment the right pointer because current records are not matching. But if we increment the right pointer, maybe next record matches. And this is possible because the data sets are ordered, they are sorted. We increment the right pointer, it moves to the key 107. Now 107 also does not match this record, but now left pointer, the left key is a smaller. So we will increment the left pointer because the current row is not matching, it is a smaller. Maybe the next record matches. So let's see that. So we forward the left pointer to the next record. Now the keys are matching, so we produce the output and we increment both the pointers. And the process continues till we reach the end of one of the data sets for inner join. For full outer join, we will have to, for any outer join, like full outer or right outer or left outer join, we may have to iterate through the remaining rows as well, which we are not showing here for simplicity. Now, taking the benefit of sorting, we know when a certain key won't be found anymore in the other data set. So we stop comparing and we move to the next record. So as a matter of fact, only a part of the data sets are compared against each other. It's not like we compare one row from the left data set with all the rows on the right. No, that's not the case. We know when to, we have the information when a key will no longer match and we increment it. And we move the pointer always in the forward direction. We never go back. Hence, if there are no duplicates, we don't go back. If there are duplicates, then things become a little bit more involved. How that looks like, it is covered in the appendix of the slides. So feel free to consult the appendix of the slides. It has more information on what happens if there is an outer join, or what happens if there are duplicates. And as a matter of fact, in the previous join, when we saw the use of hash map, what happens if we have a outer join, like a full outer join on the using hash map? So those things are also covered in the appendix. But coming back over here, we have no duplicates and hence pointers never go back, they only move forward. Instead of scanning the full data set, we know which part of the data set can potentially match the other part of the other data set. So the footprint looks like this. For the runtime, first we have to sort both data sets. So it's like m log m for the orders and n log n for the customers. And then a linear time for joining m orders with n customers is involved. We have a linear time plus some time required to sort the data sets. If data sets happen to be sorted, then we need just a linear scan of both data sets. The storage is constant because we keep track of a fixed number of variables. We are not having any inner loop or any nested loops. So the storage footprint is also minimal, and the runtime is a little bit higher than using the hash map approach. But this mechanism works without fitting any of the data set in memory. And if your data set happens to be sorted, then there is no need to sort them again, and we end up having just a linear runtime. The upsides are it works for data sets of any sizes. No need to keep anything in memory. It is optimal if data sets are already sorted on the join key, and it can address both inner and outer joins. The downside is if one of the data sets is a small, then creating the hash map approach may be faster. The other downside is it works only for the equality. For non-equality condition, again, it will fall back to our first approach where we do all, where we repeat searching for one record against all the other records in the right data set. So this downside also applied to the hash map approach. Now, before we translate our intuition on large data sets, that's what we will be doing. We let us take a look at how does join look like in MapReduce. Again, we have two data sets. Let's say these are data sets. They need not to be ordered. They need not to be sorted. For some orders, let's say it is divided, it is decomposed into two smaller files. These could be two blocks as well, which happens in MapReduce. And for the customers data set also, it is decomposed into two small blocks. There could be thousands of blocks depending on the size of the file. Now we have to join these two blocks from the orders with these two blocks from the customers. What happens in the first step of MapReduce is the mapper, which reads the input file. In this case, we produce the key and value. The key has to be the join key, and the value has to be all the columns which we want to see in the final output. So when the mappers operate in parallel, from the orders table, they will take the user ID and the order value, and from customers, they will take the user ID and the country of the customer. So mapper don't do much in this case. They simply read the value and produce the key value output. Then in the reducer, as we know, based on the hash modulus of the key, different reducers will be selected. So all the values coming from output of different mappers will be collected together in the shuffle step, and they will be passed to the reducer. Reducer at index 0 will receive all those keys where hash modulus with 3 is 0, assuming we have 3 reducers. Similarly, for reducer 1, it will receive all the keys with all the values coming from all the output of the different mappers, where hash modulus of the key gives 1 when the hash modulus is performed with 3. And similarly for reducer index 2. So all these reducers will receive values in parallel as a part of the shuffle step. And if you see, for each key, we have the information coming from both data sets. For 102 user ID, we have one value coming from the left data set and one value coming from the right data set. For some of the keys like 105, we have value coming only from one of the data sets because there is no matching entry in one of the data set. Now when we have values coming from both data sets, we can generate a record. That's quite simple, but there is a catch. Number one catch: the order of values is not guaranteed. The order of keys to the reducer is ascending. Again, I think 105 should come before, but let's take a look at this reducer. The order of the keys is ascending, but the order of values is not guaranteed. Like in this case, the GE from the right data set comes first, whereas in this case, 550, which is from the left data set, comes first. So the iterable of values from both the data sets are not guaranteed to be having in any order. Well, in this case, we can say like, okay, the string values are from one data set and the integer values are from the other data set. Well, that's a brave guess, because what happens if both the values from both the data sets are of the same type? Then we will be clueless. We won't have any idea from which part or which data set a value is coming. Let's take a look at that as well. So let's say we have customers where we don't have the country of the customer, but we have a height of the customer. In this case, if we continue to join, we have values, both the values are integers, and here it is very difficult to say which value is coming from which data set. Are both values coming from the same data set, which is possible in case of duplicates, or are these two values coming from different data sets? If these two values are coming from different data sets, which value comes from the left and which value comes from the right, we can't tell. So in order to remove this ambiguity, we tag the values. So in the output of the mapper, we don't generate a single value. Rather, we tag the value with some identifier to tell like, hey, this value is coming from this data set. So instead of returning key and value like this from the mapper, we can generate a value which is a composite of the actual value and an identifier, like from where it is coming. Similarly, if a key value is coming from the right data set, we can have output like a key and the value, which is again composite value of the actual value and an identifier. Now, with this identifier, we can understand whether a value is coming from the left side or the right side. This identifier can be anything as long as it is unique for different data sets. And this is where tuple tag is used. We discussed about tuple tag in the previous video as well, but in aggregations, it may not be super evident like why tuple tag is used, but in joins, they are essential. So here, mapper which operate on the orders data set will generate L as an identifier, and the mapper which operates on the customers data set will generate R as the identifier. These identifiers can be anything. It can be X and Y, it can be O and C, O for orders and C for customers, as long as they are different and we can uniquely identify a value. The actual string of the identifier is not important. Now we have all the values collected at the reducer for each key, and we know which value is coming from which side. Next, the reducer can operate on all the values and generate the final output. Like we have for user ID 102, what is the value on the left side and what is the value on the right side. So we can generate the final result. For some of the data, for some of the keys like 105, we don't have any value on the right, on the left side. For 106, we don't have any value on the right side. So if it is an inner join, we do not produce their output. If it is an outer join based on the left outer or full outer or right outer, we may or may not generate value. We may or may not generate the output records, but that is something which depends on the type of the join. For inner join, we will not produce any output for keys which have records missing on either of the data sets. So this is how the map, reduce, and shuffle. Well, shuffle is called shuffle and sort. So because the output of shuffle and sort is sorted based on the ascending order of the keys before it goes to reducer. So it is called shuffle and sort. So this is how the three different steps look like in map reduce when we try to join. One mechanism to if you remember, we talked one thing, that most of the optimizations of map reduce is around eliminating or reducing the shuffle, because this shuffle stage is quite expensive in terms of time. It increases the runtime because data has to be transferred from one machine to the other machine. There is a network transfer involved, which is not always the most efficient way. So one variation of join is the broadcast join, where we don't use any shuffle inside. Map reduce does the join operation in the map phase itself. There is no reducer, there is no shuffle involved. But this happens only if one of the data set is small enough to fit in memory. As we saw while developing intuition, that if one of the data sets is small enough to fit in memory, we can construct a hash map of that. So we use the same intuition over here. Let's say the customer's data set is small to fit in memory. What we do in the first stage is we create a hash map of that customer's data set. And let's say the orders data set is huge, which many a times is the case, because orders data set can be like, there could be billions of users, there could be billions of orders, but there could be hundreds of thousands of users. And if we take only a specific fields of the user or only the specific fields of the customer, that data set is further smaller in size. So if this is a possibility, what happens is there could be multiple mappers running on different parts of the orders table or the orders file. There could be again hundreds or thousands of mappers, depends on how big the file how big the actual file, or how many files the directory has. Basically, based on the size of the orders data set, there could be multiple mappers running. And each mapper will be passed this complete hash map for the lookup. Now, each mapper has a part of the orders data set and the complete hash map against which lookups can be performed over the user ID or the customer ID. And the output will be generated. This lookup operation is very similar to the second intuition we already discussed, where we use a hash map to store the smaller data sets in memory. There is no shuffle involved. It works fine for left outer join. In this case, it works fine for inner join. It does not work the same way for right outer or full outer join. However, there is a possibility to do that, and that is discussed in Appendix. Everything happens in the map phase. No reducer, no shuffle. Now, what if both data sets are huge and none of the data sets can fit into memory? This is where we can perform sort, merge, bucket join. We can take advantage of the sorted layout of the data. So the first thing we will do is we will sort both the data sets. We know how to do that. We can run a map reduce job which sorts both of the data sets. That's the one thing. And if the ordering and hashing is on the same key, then if the join keys have been partitioned into compatible number of files, also called as buckets, using the same hashing, and join keys have the same type, then we know which files have the corresponding keys. I will explain this, but I'm just demystifying things or just giving you the spoilers ahead on what to expect next. So I will simply repeat it. If the join keys have been partitioned into compatible number of buckets or compatible number of files, we will understand what this compatibility means. And if they use the same hashing, we will also understand how different hashing can make things different. And if join keys have the same type, the same data type, if those conditions are met, then we know which files have the corresponding keys. So we don't have to look up against the entire file, but we can smartly understand or guess which part of the file will match the other part of the other file. So we will explain these concepts now. Let's say we have two files, and these are simply numbers. You can think of these as to be user IDs also. For simplicity, I'm removing other fields like country and order value. They are not relevant for this discussion, but assume that they are also present in the data set. So let's talk only about the keys, only the numbers, only the user IDs for now. We have two data sets. Both sides have integer values. For simplicity, let the hash code of the number be the number itself. That is, the hash code of the integer is the integer value itself. And we partition both of the files into two buckets, which means odd values will go to bucket number 0 and even values will go to bucket number 1. Quite simple to understand, because for odd values, the hash code will be the odd value, and we perform a modulus 2, then it will give us 0. And this is how it will look like. Bucket 0 of both the files will contain odd values, and bucket 1 will contain even values. Now, if there is any value in this bucket, bucket 1, if it is present in the other file, we need not to look into all the buckets. Bucket 1, if there is any record, any number in this bucket 1, if it has to be present in the other data set, it will be in the bucket 1 itself. It won't be in the bucket 0, because we have that partitioning guarantee. Both of the data sets have only integers, and they have been partitioned using the same hash code formula, and they have been partitioned into the same number of buckets. Now, we continue on the same logic. And this time we partition the data sets into 3 buckets. So this is how the division of data will look like. Again, we can check that if any record, any data which is in bucket 0, if it is present in the other data set, it has to be in bucket 0. For example, 105. If it is in bucket 0 of this data set, if 105 has to be searched for, if this has to be looked for, it will be in the bucket 0 of the other data set. If 102, which is in bucket 0 of left data set, then in order to be present in the other data set, it has to be in bucket 0. If it is not in the bucket 0, it means it is not in the whole file itself. So what we are going to do is, if we have 2 large data sets, let's say 1 terabyte each, let's assume that the join column has random values, there is no skewness. If we create 8192 buckets, which is 8192 buckets, then, and all the buckets are partitioned on the join key, then each bucket will be roughly 128 megabytes, assuming uniform distribution of data. And all these buckets can now be joined in parallel. It will be bucket to bucket join. As we have already seen that if the criteria is met, what are the criteria? The join key, which is this, has to be of same type. They have to undergo the same hash logic, and they have to end up into compatible number of buckets. For simplicity, both of the data sets have been partitioned into same number of buckets. But buckets can be different as long as they are compatible. We will discuss that towards the end. Let's continue our discussion with equal number of buckets, which are always compatible. If that is the case, bucket 0 needs to be joined with bucket 0, not with all the other buckets. Similarly, bucket 1 needs to be joined with bucket 1, because that is where any possible match will be. Now, hash code is important. We will talk about that as well. For a given key, the partitioning strategy, whatever partitioning strategy we choose, they should give the same hash code for both the data sets. Let's say, for what happens if they are different? Let's say for the left data set, hash code gives the integer value, and for the right data set, the hash code gives is calculated using this formula: a square root of the number multiplied by 10, and you cast it to integer. In this case, even if both data sets are partitioned into same number of buckets, that is compatible number of buckets, and even if the keys happen to be of the same type, that is integers, they will end up in different buckets, and there won't be any one-to-one correspondence between the buckets. Let's see that in action. Let's say we have this left data set. The keys are present. The hash code of the key happens to be the key itself for integers. And when we perform a modulus operation with 2, assuming we are splitting them into 2 buckets, these are the bucket index where the data will go. For the right data set, our hash code formula is different. So each key will give different hash code than the left data set. And the bucket index where they will end up is also calculated here. Now, for the left data set, this is how the partitioning will look like. All the odd numbers in bucket 1 and even numbers in bucket 0, because the hash code was equal to the integer itself. And for the right data set, this is how the distribution of keys will look like. Now, if you see 100 and let's pick 106. 106 is present in bucket 0 of left data set, and it is present in bucket 0 of right data set. But what about 104? This is present in bucket 0 of the left data set, but it is present in bucket 1 of the right data set. So there is no one-to-one correspondence between the buckets. In this case, if we have to join these 2 data sets, we cannot do bucket to bucket join, because some values of bucket 0 in the left data set are in bucket 0 of right data set, and some values are in bucket 1 of the right data set. So if there are more than 2 buckets, then in that case also, one bucket has to be consulted or has to be compared or looked against all the other buckets. So it will fall back to the traditional original map reduce paradigm, where we will have to undergo shuffle in order to collect all the matching values for the key together to the reducer. So bucket to bucket join is not a possibility in this case. The other thing we talked about was the compatible number of buckets. We said that the number of buckets need not to be equal as long as they are compatible. Compatibility means one data set can be decomposed into number of buckets, which is an integral multiple of the number of buckets of the other data set. Let's take that, let's understand about that. If the hash code of the keys are consistently generated, if the hash codes are the same for the same data type, then number of buckets are compatible if one is the integral multiple of the other, or the number of buckets of the left data set is an integral multiple of the number of buckets on the right data set, or the other way around is also fine, where the number of buckets on the right data set is an integral multiple of the number of buckets on the left data set. That is also fine. Let's see that in action. So again, we have some numbers. Assume these are the keys, these are the customer IDs. For the right data set, we decompose them into 8 buckets. And for the left data set, we decompose them into 2 buckets. The hash code is the same. In this case, hash code happens to be the integer value itself. Now, if we understand this, there is no one-to-one correspondence, but there is one-to-n correspondence in this case. Let's see that in action. The bucket 0 contains 102. On the right side, there is no bucket, there is a bucket number 6, which contains 102. Bucket 0 contains 106. And on the right side, there is bucket 2, which contains 106. Similarly, 108 and 104 are in bucket 4 and bucket 0 respectively. So bucket 0 can be matched against bucket 0 on the left side can match against bucket 0, 2, 4, and 6 on the right side. Any content of bucket 0 will not be present in all the remaining buckets, which is bucket 1, 3, 5, 7 will not match against bucket 0. Similarly, the content of bucket 1 on the left side, you can validate, will match against bucket 1, 3, 5, and 7 only. They will not match against any other buckets. So there is a formula for that, which we will shortly see. So let the number of buckets on the left side be m and on the right side be n. And let's say n is more. However, m can also be more. But in our example, n, that is the number of buckets on the right side is more, such that the number of buckets on the right side is an integral multiple of the number of buckets on the left side. In this case, one bucket on the left corresponds to k buckets on the right. This is what we have seen. One bucket on the left data set will matched against 4 buckets of the right data set. Let's quickly go back here. Bucket number 0 could match against bucket number 0, 2, 4, and 6. One bucket will match against 4 buckets. Similarly, bucket 1 on the left matched against bucket 1, 3, 5, and 7. Again, 4 buckets on the right side. So one bucket on the left will correspond to k buckets. In this case, k is 4, k buckets on the right side, such that bucket index I will on the left will correspond to bucket I, m plus I, twice of m plus I, thrice of m plus I, and till the end, till k minus 1 into m plus I bucket on the right side. So what this means is, here m is 2, number of buckets on the left is 2, number of buckets on the right is 8, which is n is 8. K is 4 because 8 is 4 times 2. So one bucket on the left matches 4 buckets on the right. Bucket 0 matches, again, I is 0, so it will match 0. M plus I will be 2 plus 0. twice m plus I will be twice into 2 plus 0. It will continue till 4 minus 1 into 2 plus 0. That is buckets 0, 2, and 4. Buckets 0, 2, 4, and 6 on the right. Similarly, bucket 1, using the same formula, will match buckets 1, 3, 5, and 7 on the right. If let's take one more example. Now, this time, bucket left side has been divided into 3 buckets, and right side has been divided into 6 buckets. When I say divided, it means partitioned into 6 buckets. We already know how to create bucketed output, as we saw in the previous video. In this case, they have compatible number of buckets. Again, number of buckets on the right side is an integral multiple of number of buckets on the left side. I'm showing examples where the number of buckets on the right side is more, but it can be other way around as well. Number of buckets on the left side can also be more, and the same concept and logic will apply. In this case, m is 3, n is 6, k is 2. So one bucket on the left will match 2 buckets on the right. And we can verify that as well. If you look at here, you can pause the video and you can verify that bucket number 0 on the left will correspond to bucket number 0 and bucket number 3 on the right. If there is any content in bucket number 0, if it has to match, it will match only against these 2 buckets. There won't be any other bucket holding the content of bucket 0 on the left side. Similarly, for bucket number 1 on the left side, if it has to match any content on the right side, it will be present in bucket index 1 and 4. And for bucket index 2 on the left side, if any content has to match the right side, it will be present in bucket index 2 and 5 of the right side. And we can use the same formula and we can decide that bucket number 0 will match 0, and 0 plus I is 0, m is 2, 2 plus 0. And here k is 2, so 2 minus 1 is 1. So this part will terminate when k is 2. So bucket 0 will match bucket 0 and 3 on the right. Bucket 1 on the left will match 1 and 4 on the right. 2 will match 2 and 5 on the right. So again, there is no one-to-one correspondence, but still exists a correspondence. It is a 1 to n correspondence. There is no random ordering of the data. Because of the partitioning guarantee, because of the guarantee from the consistent or uniform hash code, and as we know that the content are of the same data types, we can eliminate joining one bucket against all the other buckets except for the matching buckets. So now let's take a negative example. This is an example where the number of buckets are not compatible. Left side has been partitioned into 3 buckets and the right data set has been partitioned into 5 buckets. If this is the case, if you see, there is no bucket correspondence between the 2 data sets. Bucket 0 on the left has matching content in bucket 0, 2, and 3. Bucket 1 on the left, you can verify that, has matching content in bucket 1, 3, and 4. Bucket 2 has matching content on bucket 1, 2, and 4. So there is no formula, there is no pattern in that, and hence we cannot be smart in eliminating any buckets while joining. So if we have to join bucket 1, we will have to scan through all the buckets. Essentially, we don't know which bucket to eliminate. We don't have a luxury now if the number of buckets are not compatible. So in the examples, we saw right side has more buckets, but left side can also have more buckets. One thing which Scio does to ensure that the number of buckets are compatible is called power of 2. Scio tells us, or basically it enforces us to partition our data sets into number of buckets, which is an integral multiple of 2. So we can choose either 2 buckets, 4, 8, 16, 32, and so on number of buckets, as long as it is a power of 2. The benefit with this approach is, since all the data sets will be partitioned into power of 2, bucket number of buckets will always be compatible. So you can take any two numbers from this series and they will be an integral multiple of each other. There will be an integral multiple of the other. For example, if you have one data set which has 8 buckets and the other data set has 32 buckets, then yes, they are compatible. You can pick any two numbers from this series of power of 2 and the number will be an integral multiple of the other. In this way, we always have a bucket compatibility if the sort merge, if the sorted buckets were generated using Scio application. If you have to select or choose how many buckets to use, usually you choose a size such that each bucket has 128 MB of data or 256 MB of data. This comes traditionally from HDFS, which is the Hadoop distributed file system. The block size used in HDFS was 64 MB to begin with. And then in later versions of HDFS, it was 128 MB. And some systems started to use 256 MB also. With blob storage like S3 or GCS, this may no longer be relevant, but still 128 MB or 256 MB as the size of one bucket is a reasonable convention. The idea behind the size of the bucket is, since each bucket will be processed by one mapper, the size of the bucket should not be too small. In that case, it won't be an efficient use of the mapper, and it should not be very big either, because in that case, mappers won't be able to split the processing further. And this is more true for the blob storage. For HDFS storage, you can have one big file read by multiple mappers, but for object storage, this is not the case. You have one mapper reading the complete file. So 256 MB usually is a good bucket size. 128 MB is also widely used. So you can try to run applications and see the performance to get an idea of what is the sweet spot. So for example, if your overall data site is 100 GB, yeah, one more thing, choose the number of buckets which is closest in the power of 2, because Scio enforces the number of buckets to be a power of 2. So for example, if the overall data site is 100 GB and you want each bucket to be approximately 128 MB, then you can choose a number of buckets to be 800. So you choose the power of 2, which is close to 800, which happens to be 1024. That is the number of buckets you can select if your overall data set is 100, if your overall data set size is 100 GB. Now, what we have seen is, if the join keys have been partitioned into compatible number of files, or that is also called buckets, using the same hashing, and if join keys are having the same type also influences the hash code. If two values are of different data types, like one is integer and one is a string, even if they contain the same value, their hash code will be different. So hash code is influenced by the hash type. Hash code is influenced by the data type. So if two data sets have been partitioned on the join keys into compatible number of buckets using the same hashing, and they are having the same type, then we know which files have the corresponding keys. So this is what we talked about in the beginning of this discussion. So hopefully now it makes sense, like what I was trying to convey. Now, on top of it, if both the buckets, if buckets on both sides are sorted on the join key, we can do a sort merge join on the bucket level. So there will be a bucket to bucket join, and then there will be a sort merge join. Sort merge join, as we have already seen, is very efficient. It finishes in linear time, and it does not use enough, it does not use extra, it does not use more memory. It uses finite number of variables to do that. So a sort merge join can be done directly on the corresponding buckets. And that is why it is called sort merge bucket join, because we are doing a sort merge join on buckets, on the corresponding matching buckets. So how will it look like is, let's say we have two files, two buckets for the orders, and we have two buckets for the customers. The data has been partitioned using the same partitioning strategy. The data types of the join key is the same. And we have generated the sorted bucket output on both sides. In this case, one mapper can take the corresponding buckets from both sides, that is bucket number 0 from both sides, and another mapper can take bucket 1 from both sides, and they can perform sort merge join operation, as we have already seen. And that is your final joined output. No need to shuffle, no need to perform any reducer step in the mapper phase itself. Just by iterating through left and right files, which happen to be buckets, which are already sorted on the join key, we end up having our result. Now, what are the conditions? Join keys have to be partitioned into same number of files. How does Scio do that? We will see demo. The sorted bucket IO write has all the configurations. The power of 2 helps maintain the bucket compatibility. Join keys should have the same type. We have the control over type of field. So whenever we generate the sorted bucket output, we have seen the demo in the previous video. As we generate the output, we can perform translation. We can do a casting of the types if they are not the same. Join keys have to be sorted. And while producing the sorted bucket output, write method does this for us. Let's see a demo. First, we will run a regular join. So I have the SBT shell, and let me run the regular join. We will see the source code as well in a while. Let me relaunch. So I'm going to run a regular join. We will discuss how the source code looks like. In the regular join, we pass the aggregated output, the total sales, and we pass the customer's data set. Both are text files. And then the output of the regular join will be stored at this location. So let me set the runners. And then I'm going to run this regular join. I will run a regular join, and then we will also run SMB join to compare the difference. I've started this. It will take a while to launch. Meanwhile, this is our Flink UI. Right now, there is no job which is running. Okay. Let's go to the code of a regular join. What happens in a regular join is we read the total sales, like what was the total sales for every user. And this is the builder. Since it was a text file, so we parse the user ID and the total order, and we create an S collection of total sales. Similarly, we create an S collection of the customers by reading the customer's text file. This is this argument will be passed from the command line, and so will be this argument. We set the user ID and country by parsing it. And then what we do is we perform a key by operation on the total sales. We key by user ID. basically we key the customer's ID also by user ID. So we have two S collections, two pair key value S collection, and we join these two using a function which is provided here. So we take the user ID, we take the total sales and customer, and we generate an output of this object. We generate an object of user sales country, which has user ID, which has total order, and which has the customer country. Whatever is the output, we save as a text file. So this operation is performing a join. This join is supported by Scio, and this join basically does does a shuffle inside. Okay, let's go back to the CLI. Let's just go to the UI to see if it is running, and it has started. It will take a while. Meanwhile, let's go to our source code for SMB join. So what will happen in SMB join, how the syntax looks like, how the SDK looks like, let's take a look. In SMB join, we call the method sort merge join. Inside sort merge join, we provide our inputs. In this case, we have two inputs, and both the inputs are Avro files. So this is one input, and this is the other input. This part. We provide what is the type of the join key, which happens to be integer in this case. And we also provide a parallelism. We will talk about parallelism after the demo, but let's keep it max for now. So we read the first input, which is the total sales SMB. This is the sorted bucket output, which was generated in one of the earlier Scio jobs. While reading, we provide a tuple tag as well. Remember, it is important to identify from which data set the values are coming. So it is good to associate a unique ID for records coming from a specific data set. So you can choose any arbitrary string here. I have chosen LHS, which is fine. And you specify what is the class, what is the schema of the data contained in that file. Similarly, we read the other data set, which is the customer's data set. And this syntax may not be new to us. We have already seen this syntax before. And the new thing over here is we pass the tuple tag. So here the tuple tag is RHS for customers data set and LHS for sales, total sales data set. And we save things as a text file. We can also save it as a sorted bucket output. That is also possible. But here, just for easy readability, I'm saving it as text file because I don't intend to use the output for other applications. But if you intend to use output for other applications, you can do that. Now, here, once you read the input, now you have to provide a logic for joining it. And that is what we are providing in the map function. So this function receives an integer and a tuple of total sales and customers. Integer is what the join keys value is, and total sales and customers are the value coming from the left and right side respectively. Once we receive those values, we simply create an object of user sales country, which has got a user ID, so sales and country information. Now, let's go back to the terminal and see if it is still running. On the UI, it is still running. That is fine. Once it finishes, we will run our SMB. We will run our SMB join, where we will pass the sales data set. This was produced as a part of the SMB aggregate, where we performed an aggregation over the user ID and did a sum total of all the order values. And this is the SMB data set containing the customer's information, the customer ID, and their country. And we want to save the output at this location. Other arguments are not new. They are, I guess we are already familiar with them. So I will copy this. Okay, this is still running, so no rush. Let it run, let it finish. And once it is done, then only we will go and run our SMB join. But let's go back to the slides then. We will come back to the demo. Here, ordering needs to be consistent on both sides. We have seen that the ordering which is observed from the sorted bucket output in Scio is not what the natural ordering is. But as long as both the data sets have been generated using the same ordering, and it is one application which is generating the output and reading those output as input for the subsequent jobs, everything is fine. So what we have seen is we can read the sorted bucket using a sorted bucket io.read. For example, this is for Avro. We can use a tuple tag to distinguish between records coming from different sources. While reading, we filter. There is also support for with predicate. If you want to filter out records, you can use with predicate. This is very true for reading Parquet files. You can skip reading records when you are constructing the S collection itself. And because this filtering happens on the data side, on the actual data storage side, this makes things very efficient if you have to filter out some records while reading. We call the method sort merge join to do the inner join. And in that case, we have access to the key as well as the values of the key from the different sources. We can set the parallelism of the join operation. We will see that soon. As of now, we have set that target parallelism to be max. Over here, we choose the target parallelism to be max. We will see what max means later. And then we supply the type of the key as the argument for sort merge join. We have seen how to generate sorted bucket output and how to perform joins between sorted buckets. There are other methods also available, which are also provided by the API, is group by key, sort merge group by key, where you can get access to all the values for a given key. Then there is a sort merge co-group, which gives all an iterable over all the values coming from all the sources which you want to join. We will talk about parallelism, but let's go back to the CLI and see what's happening. Okay. So the regular join is still running, and let it run. I will pause the video for a while because I want to start parallelism after we start SMB joins. So I'm pausing the video for a while and I will resume it once it is done. So it took little less than 8 minutes to finish and the regular join has completed. Now I am going to run SMB join. Let the join run. We will compare the output. We will also compare the runtime to see if there is any difference. And we will also take a look at the job graph. So this was the job graph of regular join. Again, quite a broad job graph because we are joining two data sets. So it's a little bigger than the job graphs we have seen before. If you are interested, you can drill down into them and you can try to inspect what each box was doing. Okay, coming back to the parallelism. Meanwhile, let it run. We will see this later. Now, let's say the left data set and the right data set have compatible number of buckets. Left data set has 2 buckets, right data set has 8 buckets. And the type of the key, type of the join key is integers. They have been partitioned in using the same hashing strategy. So it means the number of buckets are compatible. And this is a candidate of sort merge bucket join because the join keys are sorted as well. Now, what happens next is when we have to join this, one option is we can have the number of mappers equal to the number of smaller buckets. In this case, the left side has lesser buckets and right side has more buckets. So left side has 2 buckets. So we can launch 2 mappers, 1 mapper for each bucket of the left side. And then each mapper, like the mapper which takes bucket 0 of the left side, will read the corresponding 4 buckets on the right side. And the mapper which reads the bucket 1 of left side reads the other 4 corresponding buckets of the right side. This kind of parallelism is called min parallelism. In this case, the resource requirement is less because we are using the number of mappers which equals the number of smaller buckets of the either data sets. But the throughput is also low because each mapper, like if you see this mapper, it ends up reading 5 buckets, 1 on the left and 4 on the right. So both mappers are reading 5 buckets overall. So the throughput is less, but the number of mappers which is needed is also less. The other extreme is the max parallelism, where more resources are needed, but it gives high throughput. In that case, what happens is we choose the number of mappers which to be equal to the number of buckets which is larger. So on the right side, we have 8 buckets. So we use 8 mappers, each mapper reading 1 of the buckets of the data set having a large number of buckets. And then each of the bucket on the left side is replicated to each mapper. So if you see, each mapper ends up reading just 2 files, one from the left and one from the right. And the one of the file from the left side can be replicated to all the corresponding mappers which read the corresponding buckets. Similarly, for bucket 1, the mappers which read bucket 1, 3, 5, and 7, they will receive a replicated copy of this bucket. So in this case, each mapper is reading just 2 files, not 5, and hence the throughput is higher in this case. However, there is one catch. For inner join, everything is fine. But for outer join, this setup needs a little bit of care. How? Let's take a look at that. Now, in this case, let's say bucket 1 was replicated to 4 mappers, where each mapper was reading a corresponding bucket from the right side. So let's focus on this part only. And the same thing applies for the bucket 0 of the left data set as well. But let's see this example. So after replication, this is how it will look like. Bucket 1 has been replicated 4 times for each mapper. If it is an inner join, then this mapper will not produce any output because there is no match. This mapper will generate an output. This mapper will also generate an output, and this mapper will also generate an output if there is match. Everything is fine. There is no problem. I think the output looks fair. But what if there is a left outer join? In left outer join between these 2 buckets, all the rows, all the records from the left side which do not have a match, they will also be present, which means something like this. You have all the values from the left side with a null value for the right side. Similarly, the matching keys will have values from both sides, whereas any key which does not have a match on the right side will have null for the right side. So all the values from the left side will be present. If there is a matching value, if there is a matching key on the right side, that will show up, else null will show up. So same with this case as well. Now, if you see something, there are a lot of duplicates. Like for key 101, it comes 4 times. And the final output is not accurate. You will have to discard the duplicates. You will have to keep one value and you will have to discard the others. Deduplication is quite expensive. A cheaper operation is rehashing. What happens in rehashing is, if one bucket is matching more than one bucket, And if we are doing a max parallelism where this bucket has to be replicated, we rehash the content of this bucket into 4. So we rehash the content of this bucket, assuming how would the distribution have looked like if there were 8 buckets. I will repeat this part. The right data set was partitioned into 8 buckets. The left data set was partitioned into 2 buckets. But now we are choosing a max parallelism, which means the content of this bucket will be replicated. And as we have seen, because of replication, there will be duplication for the outer join, for the left outer join specifically. And running a deduplication is expensive on the large volume of data. So what we do is we repartition the content of this bucket only, assuming how would the distribution have looked like if there were 8 buckets. So we end up creating 4 buckets out of 1 bucket. And since the left data set has 2 buckets, overall it will end up splitting into 8 buckets, where each bucket will split into 4. Why? Because each bucket has 1:4 correspondence, like 1 bucket is matching 4 buckets. So we split this bucket into 4 buckets with the intent, or with the expectation, like how the distribution would have looked like if it was divided into 8 buckets. And we choose bucket index 1, 3, 5, and 7. Now we can do this one-to-one join in the mappers. And now we can do outer join, inner join, any other join is possible. So we will just have to do a rehashing. Now, min and max are on the extreme. A middle ground is auto parallelism. So we can have 4 mappers, neither 2 nor 8. In this case, we can do things with 4 mappers, which is a middle ground between how much data has to be rehashed or replicated. This will have the resource requirement and throughput in the middle of both extremes. So parallelism has got 3 possible values as use. Okay, something failed over here. We will take a look at that. But before that, we have target parallelism as max. There are other values as well. There is a value of auto, and then there is also a possible value of min. So these are the 3 different values for the parallelism. Here we choose our parallelism to be max, and that was because we wanted to have higher throughput. So there is some failure here. We can check the logs. Okay, something failed. I will pause the video. I will try to fix this and then resume it. Maybe I'm losing some network connection to my VM instance. Okay, so both the jobs have finished. The problem was with my Docker container. It was stopped somehow, but then I resumed Docker container by running the Docker commands. We have already seen the Docker commands in the previous video. So we have run the regular join and the SMB join. As we can see, SMB join takes lesser time than the regular join. The difference here, however, is not huge. It's roughly 10% of a difference, but it depends on the volume and the shape of the data. The difference in the runtime can be considerably, it can be very, very different. However, one thing to note here is, let's take a look at the job graphs to see what was the impact on the SMB join as compared to the regular join. As you can see, this regular join has more steps than the SMB join. You can count the number of steps as well. And this is because SMB join does not involve any shuffle. Overall, based on the shape of the data, in extreme cases, we have observed 80 to 90% of reduction in the shuffle because of the SMB join. The runtime difference may not be very huge, but when you are running applications on cloud providers like Dataflow or AWS Glue, over there, how much data gets shuffled has a direct impact on what is the cost of the job. So SMB join not only helps you achieve better runtime, but it also helps you cut your costs you spend on your data processing infrastructure. Now, we will take a look at some of the records of the output. I have chosen one user ID. For this user ID, I will check for what was the output in the regular aggregate output. This was created in the previous video. We will check the customer information and we will see what is the output in the join. Okay, let me run these one by one. So this user has this information in the regular aggregate output, which means this user has a total order value of 224. This user belongs to Brazil. And in the join output, hopefully we should have both the information, and we do have that. We have the user ID having a total order value of 224 belonging to Brazil. And let's compare let's take a look at the same information from the SMB join output. So on the SMB join output, if we check, we get the same information. So we have validated for one of the users that it has the same content across both data sets. But when you run this, you can also do your validation. And that was mostly it about SMB join. Just to conclude, we were talking about parallelism. We talked about min, max, and auto parallelism. And SMB is not a new concept. It is already there in a lot of systems. Spark SQL supports SMB join. There is a Medium blog post I have linked here. Flink uses SMB join, sort merge join as one of its internal strategies. Again, the link is here. Hive, which is a SQL wrapper on top of MapReduce or other processing frameworks like Tez and Tez. It also uses sort merge join, which eliminates shuffle. There is a LinkedIn blog post here. Presto, I guess it is not implemented yet, but there is a PR which introduces merge join in the query plan. But the implementation at the time of recording this video is not yet complete, but you will find more information about what is the current progress of a Jira ticket. So the community of Presto is aware of possibility of using SMB join because of its benefits, but and hopefully it gets implemented in future. One more thing to conclude, in Scio, there are a bunch of joins. I have added the link to the documentation. There is a large hash join. In Scio, we have a SMB join, we have a hash map join as well. And the regular join, which uses shuffle, is also there. There also is a large hash join, which uses a Sparky file, which is a disk-backed hash map. Or a disk-based map data structure. If you remember, one of the data sets was small enough to fit in the memory. We used a map side join or a broadcast join. Here, in large hash join, even if the data cannot fit into memory, we can create a Sparky file. This is good if the data set is of medium size. That is, a data set is not too huge, like it is not in terabytes, but it is, let's say, hundreds of gigabytes. That is the scale of the data. Maybe hundreds of gigabytes is also too much, but this is something, if data cannot fit into memory and you want to still use hash map join, that is where you can take advantage of that. We have a skewed join where a count min sketch probabilistic data structure is used, which generates an approximation if a particular, how many times a key has repeated. So what happens in a skewed join is if one of the data sets has too many records for one key, Then when you go for join, the reducer, one of the reducer will get skewed because it will have lots of values for one key. In extreme cases, you can run out of memory or you can have inefficient execution. In those cases, it uses it divides keys into hot and chill zone by scanning through one of the data sets once and making use of count minute sketch to generate approximate frequencies. And then it uses normal join for the chill, which is the cold keys, and it uses a broadcast join for the hot keys. And then there is a sparse join. What happens in a sparse join is if you have a lot of records on the one side which do not match the other side, and you happen to use let's say inner join, in that situation it is good to eliminate those records on the left side for which there is no matching record on the right side. And this is done by creating a Bloom filter on the right side. A Bloom filter is again an approximate a probabilistic data structure which works on the hash code. Using that data structure, we then scan through all the elements of the left data set and we discard. The good thing about Bloom filter is it will give you a definite no. It can give you a maybe yes, but it gives a definite no. And in that situation, if there is any key on the left data set for which the Bloom filter gives a definite no, we discard those keys and we take only those records for which there is a maybe yes in the Bloom filter, which means maybe that record is present on the right side. So this was just scratching the surface of these three joins. Again, they can be discussed in a lot more detail. You may be wondering what is count minute sketch or what is a Bloom filter or what is a Sparky file. Feel free to refer to the documentation and you will find lots of great resources around it. I just wanted to mention that there are more specialized and enhanced joins in Scio. It's fine if you don't understand that. It's not related to sort merge bucket in any ways, but there is a documentation linked over here. And that was it. Congratulations on finishing this video. You have come to the end. In this video, we talked about joins, what are the common situations where joins are used, and what are the different ways we can do joins. We developed intuitions by using a nested loop join, then a broadcast join, and then a sort merge join. And then we discussed a bit in more detail about what is sort merge bucket join. So hopefully now you understand. Basically you do a bucket to bucket join if the conditions of joins are met, like same hash type, same data type of the keys have to be partitioned into compatible number of buckets, and the buckets have to be sorted on the join keys. Then we can perform bucket to bucket join. We can perform sort merge join on the bucket to bucket level, and hence it is called sort merge bucket join. Hopefully you were able to understand what the parallelism means and what the compatible number of buckets mean. With this, we come to the end of our second and final video on the sort merge join. Thank you for watching.